out of the total atmospheric pressure. So as gases have weight, they exert pressure to the surfaces in contact, which we call atmospheric pressure. And we show the atmospheric pressure at P0. Here you see the components of atmosphere, the approximately 78% nitrogen gas, approximately 21% oxygen gas, 0.93 argon, 0.03 carbon dioxide, and the rest water vapor and other gases. These are the partial pressure values and the molecular masses. So you see that most of the atmosphere is composed of nitrogen gas and oxygen a little bit less, and we have the other gases also. The value of the atmospheric pressure is 1 atmosphere, which is equal to 100,000 Pascal. So we use 100 Pascal as 1 atmosphere pressure as 1 atm. The Earth's atmosphere is about 480 kilometers thick, but most of the atmosphere, about 80%, is within the 16 kilometers of the surface of the Earth. When I say this is Earth, you may thought of the atmosphere as this. The thickness is about 480 kilometers, but as the gravity gets less, the density of the atmosphere gets less, so it is denser next to the Earth. So most of the gases, the 80% of the gases are found in this 16 kilometer part. There's no exact place where the atmosphere ends. It just gets thinner and thinner until it merges with outer space. Here you see the change of pressure with height. As the altitude gets higher, there's a decrease in atmosphere, because at higher elevations there are fewer air molecules above a given surface than a similar surface at lower levels. These are the examples to the existence of atmospheric pressure in our daily life. When we pump the air inside a container, it will shrink like this because of the atmospheric pressure. When we put a sheet of paper at the top of a glass full of water and turn it down, then the atmospheric pressure will keep the water in the glass because it is bigger than the pressure of the liquid. This is an example for cross-section of a modern drinking fountain. When the water comes from the tap, you may see some bubbles going up because there's gas here keeping the pressure as equal to atmospheric pressure. So we have atmospheric pressure at the tap equal to P0. They cancel each other, so the pressure of the liquid let the water go out of the container. And also atmospheric pressure helps us to drink by using pipes. The atmospheric pressure pushes the liquid up the pipes and help us to drink. Torricelli is the first scientist that proved the existence of the atmospheric pressure. This figures out the experiment that Torricelli has done. There is a tube full of mercury. It is in a container full of mercury. So this is done at the sea level. Here there is no gas, it is vacuum, no gas, so no pressure. He found that this height is always equal to 76 centimeters. So How this 76 centimeter mercury is balanced? It is balanced by the atmospheric pressure. We learned in the combined vessel that the points at the same level within the same liquid should be the same. Let's say A and B. You see the big large picture here. This is A and this is B. So the pressure at the point A should be equal to the pressure at the point B. The pressure at the point A is supplied by the atmosphere, so it is equal to atmospheric pressure. The pressure at the B is supplied by the pressure of the liquid with a depth of 76 centimeter mercury, which is equal to dHg. If you put the formula, the density of the mercury, 13,600 kilogram per meter cube, the height in meter 0.76 meter and G as 10, then this will be equal approximately 100,000 Pascal, which we use as 1 atmospheric pressure. So, when using mercury, instead of using atmospheric pressure as a unit or Pascal as a unit, we have another unit. We say that the P0 is equal to 76 centimeter mercury. Now let's read the unit. That means that this pressure is the pressure applied by the mercury with a depth of 76 centimeters. So let's review the mathematical modeling. The pressure of mercury with a depth of 76 centimeters is equal from the formula density depth times G. The density is 13,600 kilogram per meter cube. The depth 76 times 10 to minus 2 meter and G. So this is equal to atmospheric pressure, which is approximately 100,000 Pascal, which is equal to 1 atmosphere, which is equal to 76 centimeter mercury. So this is the value of the atmospheric pressure in many units. Why do you think Torricelli use mercury, not water? What will happen if water is used? The pressure will be the same. When you calculate from the formula, you use the density of water here, which is equal to 1000 kilogram per meter cube, the height of water times G will be equal to 100,000 Pascal. So when we cancel the zeros, the depth of water should be 10 meters. So the length of pipe should be minimum 10 meters, which is not so useful. We have some measuring devices related to the atmospheric pressure. Barometer is the instrument used to measure the atmospheric pressure. There are two kinds of barometers, mercury barometer and metal barometer. Altimeter is a special kind of barometer which measures the height of a place or object compared to sea level. It uses the atmospheric pressure. It is especially used in planes, meteorology, and by climbers. Manometer is an instrument used to measure the pressure of gas in closed containers. There are two kinds of manometers, liquid and metal manometers, and liquid manometers have also two types, open and closed end manometers. Here you see that this is a closed end manometer and these are the open end manometers. In closed-end manometers, the pressure of the gas is directly equal to the height difference in the second column, because here there is no pressure, there is only vacuum. So the pressure of the gas is equal to the pressure of the H1 depth liquid, mercury we especially use. So you can say that the pressure of gas is equal to H1 centimeter mercury. But here it is open, so the atmospheric pressure is exerted. So you see that the difference in level of the mercury is at the right side. So the pressure of the gas is bigger than the atmospheric pressure. So the gas is equal to atmospheric pressure plus H2 centimeter mercury. Here again, this is an open-end manometer. There is atmospheric pressure exerted on the right side. But this one, the difference in mercury levels is at the left side. That means that the atmospheric pressure is bigger than the gas pressure. So the pressure of the gas is equal to the atmospheric pressure minus H3 centimeter mercury. Let's do some example. The atmospheric pressure is equal to 740 millimeter mercury, and the pressure of the gas P1 is equal to, now look at the difference in levels. Which one is bigger? Atmospheric pressure is bigger than the pressure of the gas. How much bigger? 15 millimeter mercury bigger. So the pressure of gas 1 is equal to 740 minus 15, which is equal to 725 millimeter mercury. Again, here the atmospheric pressure is equal to 1 atmosphere, which is equal to 760 millimeter mercury. Again, the atmospheric pressure is bigger than the gas, so the pressure of the gas is equal to 760 minus 45, which is equal to 715 millimeter mercury. Now here again the atmospheric pressure is 1 atmosphere, which is equal to 760 millimeter mercury. This time you see that the difference in mercury level is at the right side, so the pressure of the gas is bigger than atmospheric pressure, so it is equal to 760 plus 65, which is equal to 825 millimeter mercury. Bathymeter is the instrument used to measure the depth of sea by means of pressure changes, used to examine the sea surfaces and in mineralogy. There is another famous experiment, the Magdeburg Hemisphere experiment, done in Germany by a scientist Otto von Guericke. A German physicist born in Magdeburg performed a famous experiment called Magdeburg Hemispheres. These were two halves of a large hollow metal ball you see here. When all the air was sucked or pumped out of the ball, 2 teams of 8 horses can't pull them apart. This is an imagination of the experiment, because the pressure of the Earth's atmosphere created a very, very large force on the ball. When there is gas inside the hemispheres, it is easy to separate them, but when the gas is pumped out, the pressure inside is 0. So the atmospheric pressure push the hemisphere at all sides. The value is very big. What was it? It is 100,000 Newton per meter square. That means that it applies 100,000